just to make sure that everyone get it correctly. As I mentioned last class, you can write in the chat box anytime you want. If there's any question, anything, you can just directly put it there. Okay, so last class we talked about that Ethernet and Ethernet protocol in general. What I care about Ethernet now is how the MAC address table is being built, because this is one of the fundamental issues. We need to understand it. So let's see if we have a better, this one. Okay, let's take this one. I'll take this one, put it in my coming up, so I can draw there. Let's do that. So if I have this switch, which is exactly similar to what we have in the lab, and we want to see how the device will build its own MAC address table, we need to, as I mentioned before, we need to think like the device itself. At the end, it's programmed to do things, and the protocol will help it to do that. Can anyone remember the name of the protocol to build the MAC address table? I mentioned it last class. What is the protocol that will help building the MAC address table? Anyone? So let's assume here that one device, which is having MAC address 0E, I don't know why no one answered the name of the protocol. I'll assume that you remember it. This Address Resolution Protocol, ARP. Okay. Now, let's say this 0E wants to contact or talk to a device with the MAC address 0C. Inside the frame it was sent, we will have few information stated there. We will have 0E as, 0C as the destination, 0C destination or MAC destination. And then we will have MAC for the source. Then we have IP for destination. And then we have IP for the source. Now, since we don't have anything, since we are talking only about MAC address, we don't care about the IP address yet. We'll talk about it, inshallah, this class. So if I want to write this one here, you will find that MAC address destination, what it will be?
C.
It will be 0C, because that's where we want to send the packet to, or the frame to. And then 0E will be the source IP address. IP address, we don't care. Okay, so now what will happen? We will have the MAC address table here, MAC address table. At the beginning, when the device starts, what we'll have, we'll have two information should be there, port number, and it will match it with the MAC address. MAC address, okay. Now let's make it nicer. Port number and MAC address. At the beginning, it's completely empty. By time, it will start to fill it with a few things. So now the message we are having, it will go from E to the switch. The switch will look at it. Okay, now we know the source is 0E. And we know this 0E came from F09. So before we do anything, the switch would decide that, okay, let me save this information. It will be useful for me later. So it will register that if FA fast Ethernet 9, that port, is connected to a computer with the MAC address 0E. This information will be saved. Maybe at this moment we will not use it, but it will be useful later. What will happen next is, now, do we have the destination 0C in the map, in the table? No, it's not there. So the switch simply doesn't know where to send it. What it would do in this case, just send it to everyone in every port connected to some devices. All of them will receive it, to receive a copy. We call this one flooding. We are flooding the ports. Flooding is a really bad thing. We don't want it. Why? Because simply some devices will be busy processing, the CPU will be busy processing packets which are not, or frames which are not related to them. Just they have to ignore it. Now, each of them will look at it and say, okay, this one here, 0A will look at the IP address and the MAC address. This is not mine, so I simply ignore. This one also will process it, put in the CPU, check, it's not mine, it will ignore. D also will ignore. Now, only C will look at it and say, oh, this is mine, I will reply, send a reply. So the reply will be sent from C to the device itself, or to the switch itself. The switch now will look and say, okay, I got a new information. It will be useful for me to record that information. FA port 5, FA5, is connected to a device with the MAC address 0C. Okay. Now it will know where to send it also, because it will check that the destination will be going to E. To send it from here to port F9. Now this device, maybe we never use it nowadays. This device is an old device. We call it a hop. A hop is a device in layer 1. This device simply take the message, okay, make copies, send it to everyone else. It will not even check MAC address or anything. Anything it will get, make copies, send it to all devices connect to it. That's why we are not using nowadays, because it is splitting the bandwidth very slow, making the whole network very slow. But you need to know about it, because simply some old networks maybe you will deal with one day are still using hops. That's why we need to know. So what will happen when F09 receive it? F09 here receive a message from, let's change the color because it's not clear. I'm not sure which color will be a good one here. Okay, 0C sent to the computer, to the switch recorded in here, the information, and then forwarded to port 9. When it will reach port 9, it will send it outside, connected to hop. Hop will make 2 copies, one here, one here. It will not even check anything, simply make 2 copies, one here to every device it's connected to. Now, since we have that one, if 0F is not mine, I'll ignore. The other one simply will process whatever inside the frame. So that's simply by time. The whole MAC address will have all the information about every single device connected to it. Later, flooding will be no more used, or at least it will be used in a very, very minimum, or very, very few times only. Okay, so is it clear now? Can you write in the chat box how clear is this idea of the MAC address table and how we build it? In the chat box, if you are still awake. Is it clear? Alhamdulillah. Others? Sleeping? I know it's in the morning, online class. Most of you will be sleeping. That's just normal. or should not be normal. Okay, so if it's clear, since no one is saying anything about it, let's move to the network layer, because simply that's our main layer. We are in networking class, so this is our concern. So for network layer, simply what we have, it is layer number 3. It has a few things to do. First of all, addressing using the IP address. Encapsulation means add the IP address and some more information to the packet. We call the data unit here as a packet. Then it would decide to which direction it would take that packet. When you receive a packet, you have to route it to the right place. So simply encapsulation, I can skip these things because I talked about it mostly, and some of them are not affecting our stuff. Now, for next thing, we have to know about IP address. IP address, we have two types we are using nowadays, IPv4 and IPv6. What happened to IPv1, 2, 3? Any idea? We are not using them at all. IPv1, it is the internet protocol created the first time internet was inside one lab. So the idea was we have two computers. Now these computers are having data and we need to use the data of computer 1 on computer 2. At that time, they have the punch cards. I'm not sure if anyone, I used to have one actually. Let me see if we can get punch cards to a picture of them. Punch cards. Okay, if you want to see, this is exactly how the previous computer read. So for these punch cards, I used to have many of them. All of them are considered as one. I think hundreds of them. They are in boxes. Every one of them considered as, all of them considered one program. So when you look here, you see there are some holes inside each card. These holes are, I'm not sure, is it a 1 or 0? Okay, so if there is a hole, the computer will read 0. If it's no hole, that means 1. So this is simply how the devices will read. If you want to put the input, you read it, it will read it like that. The output also, it will put some punches inside the card itself. You take it to the other computer to read that output. So the idea now, it came that why we are doing it, it's taken a lot of resources, a lot of very long time actually to do these punch cards. So what to do is someone came with the idea, let's connect the devices together. The output from one device go to be the input of the other device. And they call it internet because they want to control it, but they found they need to have like common standards between the devices. They call it internet protocol to become the standard. So at the beginning, it was only 2 devices or 3 inside one lab. That was IPv1. By time, the other lab in the same university, they want also to use it. Then they found out that, oh, no, to connect it is a little bit more complicated than 2 devices talking together. Let's make IPv2. So very fast, they did IPv2. Later, other universities and military start hearing about that. They decided to make IPv3. IPv3 was made, and everything here is very limited. Maybe, I don't know how many computers at the beginning, but we are not talking about more than maybe 100 computers all around the world connected together. By 1980s, if I'm not mistaken, when personal computer exists, now people got their computers, they want to get internet also. Personal computer was done by IBM at that time, that's company. I believe IBM now is famous with the blockchain platforms. But in general, it was the one who's making the personal computers. You can put it inside the room because before that it was very huge, need the entire room or entire like multi-purpose hall, just put one device. So when they did that, now they got many computers. To connect them, we need IPv4. So we had 1, 2, 3, 4. That was there, but 4 is the one which we believe that, okay, we can use it for a few years. before we discover that we are in trouble. Now, if you look at this IPv4, the header, when they did this protocol version 4, the header is 32 bits or 8 bytes only for address, source address and destination address. If you look here, 1, 2, 3, that will make it 6 bytes. And 4, that's 10 bytes, right? 4, 3, 7, okay. So the IP address will be 32 bits and destination IP address 32 bits. If that's the case, that means if we use all the IP addresses of the world, there will be first IP address in the world will be, as we said, 32 bits. So IP address, IPv4 address having 32 bits. So if we want to start counting 32 bits, how many devices can we have? First IP address ever will be 000.00000.000, when all of them zeros, right? That's the first IP address in the range of available IP addresses. So that's the first IP address. Second IP address, what it will be? For that, let's see, this is in binary. If I change it to decimal, it will be 0.0.0.0. Second IP address will be all zeros, except this one will change to 1. So when you change it to decimal, it will become 0001. Next, this one will become 1. Okay. And the decimal will be, what will be the decimal in this case?
0002.
0002, right? 000.2. Okay, next one will be changing. This one will be 11, which will make it 3. Okay, next it will be 1, and that will make it 4, and so on. So what will be the last IP address? What will be the last? All 1, right? 1111, 1111, 1111. Okay, if I change this one to decimal, it will be, let's bring the calculator. Although this number you should remember at all time. When you have binary all ones, 8 ones, it will be 255. That's the maximum you can get in every octet. Octet is the group of 8 bits inside the IPv4 address. So that will be 255, 255, 255, 255. The first IP address will be 000. Last IP address is 255, 255, 255. Now, if I ask how many addresses from this one to this one, how to calculate it? Since we are using binary number, so either it is 0 or 1, that will make the calculation 2 is the base to power, or what? 32, correct. 2 to power 32. Why 32? Because we have 32 bits. So if I open the calculator again, 2 to power 32, I need to go from programmer to scientific to power 32 will give us 4 billion something, something, something. Okay, so it will be around, let's say, 4 billion IP addresses, IPv4 addresses. That's how much IP addresses we can get. We cannot get more than that. Okay, 4 billion. Now, I want to Google it or ask ChatGPT, what is the population of human beings on Earth nowadays? I'm not sure how many are outside the Earth, in a spaceship maybe. But on Earth, what is the population now, today? Can you ask Google and tell me in the chat box?
Can you repeat the question, Professor?
Sorry, sister, the voice is not clear. Can you write it in the chat box, please? Okay, 8 billion. Okay, that's 8 billion population, 8.1.24. Okay, actually, every semester I ask, it will be like a huge number increased. So the thing now, from these 8 billion, how many do you think are using internet? You can ask Google if you want. How many of them are using internet? Nowadays, 1 year old having a phone, right? You can ask Google how many of these 8 billion people are using internet. You will get maybe, if we remove the rural area, the very old people, and then we remove the kids who are 1 month, 2 months old. Okay, so you can see, okay, brothers, thank you. So we have 6 billion using the internet. Okay. Now, asking you, how many devices you have connected to the internet right now? How many devices you have right now, meaning iPad, laptop, smartphone, smartwatch? How many of them are connected? 3. Anyone having 4? Some of you may have 4. Okay. So let's say
4 billion.
Okay. So let's see, 6 billions, each of them is using, let's make it 2, because some people, they have 1 devices. Let's say the average is 2, okay? That will give us 12 billions IPv4 needed. We cannot increase this one. This one, 32 bits, okay? We said the maximum we can get is 4 billion. If we want to increase this one, add more bits to get more IP addresses, we need to change all the hardware, okay? All the switches, all the routers, all the back-end, all the end devices. All of them should be changed all around the world. How many devices we have all around the world connected to the internet? I think around, you can see 12 billion device. We cannot simply wake up in the morning, say, today we will change the hardware. Software is possible. To change the software, it's possible to do. But the hardware is very, very expensive, very hard. You need technical people to do it. You need enough engineers, too many things. You need governments also to accept the budget to change the devices, because again, this is a standard. When we say IPv4, it's Internet Protocol, it means that every single device all around the world should use exactly the same number of IP addresses, should understand the IP address in the same way. If you do any changes in the device, it will not understand internet, there will be no internet. So that's the idea now. We got this problem with the IPv4. A lot of devices, okay, cool. A lot of IP addresses, however, humanity is much more. But the problem in end of 1970s, when they had the IPv4, they never thought about it. Why? It's like we have a few computers in the universities, some military institutes maybe are using the internet. So maximum we get maybe 10,000 of them. They never thought that one day everyone will have more than one device connected to the internet. So in around 1994, if I'm not mistaken, the organization, okay, one thing also, who's giving the IP addresses? There is an organization called IANA. IANA stands for Internet Addressing and Numbering Association or something. Any country wants to use the internet, they will go to IANA, ask them to give me the range of IP address. Remember, these IP addresses cannot be duplicated. It means no 2 devices can have the same IP. It's just like your passport number, your ID number. You cannot have 2 people having the same ID number. What will happen if you have that? If two people having this exactly the same ID number here in Malaysia, what will happen? You try to send a message to one of them, you try to do the tax, you try to do anything you want to do, you'll be confused. I mean, which one? The ID number should be really identifying a single person. Same thing for the IP address, identifying a specific device. No devices can have the same. So IANA, they have different organizations all around the world, each of them dealing with different countries, okay, or different continents. Some of them for Asia Pacific, some of them are for, okay, let's see. Asia Pacific, we have, where are they? I want to see, there's a map somewhere here, should be, okay, no map. For Africa, for South America, North America, Europe, that's, yeah, I think that's all, 5 of them. So the one in Asia, they were like 1994, these were the first people to say in Asia Pacific, saying that, oh, we are running out of IP addresses. I cannot give IP address anymore to any country, to any organization. Why? Why do you think Asia is the one announcing that first before Europe or America? USA? Why do you think Asia will be the one to announce that first?
Biggest population, maybe.
Yeah, you have the population of China and India is half of the world somehow, right? So Asia is the first one giving IP address everyone. It was very generous, giving everyone an IP address they want. Suddenly, they announced that IANA branch in Asia, and I don't know the name, it has a name, but I forgot it, said that we are running out of IP addresses. Now, everyone panicked, you can say. If we have no IP address, means that we cannot add more devices. We cannot sell more computers, connect to the internet and so on. So by time other countries start announcing, other continent also start announcing that, oh, we are running out of IP addresses as well. So now IETF, Internet Engineering Task Force, this belongs to ICANN. This is the internet government, you can say it, okay? ICANN is the internet government. All the money for the internet will go to these people, to the ICANN. And just for your information, you have ICANN branch here in Malaysia. You can be members in them. They call it here Internet Society. Internet Society Malaysia chapter. So these people, Internet Society, they are NGOs, people who are volunteered to help governing the internet. So if you are a member of this one and you are so active, you will go to all ICANN meetings. ICANN meetings, simply they sit and try to do the policies, they try to fix the technical issues, they try to discuss the problems we are facing or we will face in the future. So these ICANN people simply are the people to decide anything related to the internet. And these people also, if they decide something, all governments all around the world should follow. If you don't follow, simply you will not have internet in your country. So you can see they are very powerful, but they are not, supposedly, they are not controlled by a specific country, okay? 3 or 4 years ago, they had the meeting in KL. I attended that meeting. Around, what they say, 2,000 people all around the world came to discuss some issues related to the internet. And of course, some governments, they send representatives also, just to see that what we would do. So simply ICANN, they have one, ICANN, they have IANA part of it. IANA is part of ICANN. the Internet Addressing and Numbering Association. It belongs to ICANN. And also IETF, Internet Engineering Task Force. These are focusing on the technical parts, okay? Meaning the engineers will be here. All internet engineers, the technical part will be there. So now these people, when they see that we are running out of IP addresses, they call for proposals. Okay, people, we will have a problem. Give us solutions. In IETF website, if you go to it, this website is my favorite because if you do master or PhD in networking, you have to read a lot of their drafts. What is a draft? A draft, let's see, IPv4, okay, IPv4. IETF IPv4, you go there, you will see they have what we call RFC. RFC is, stands for what? I forgot. RFC stands for what? For comment, something. Request for comment. RFC is request for comment. Okay. So you will have a draft of the solution you have, a proposal saying that this is my proposal, how to solve the problem. So they will sit and the experts will read it. And then if it's valid, they will send it to RFC, request for comments, meaning that we open it now to public. Anyone want to comment about this proposal, let us know. Okay, so you see IPv4 was done in Virginia. It was proposed in Virginia 1981. So later it was updated until it became 760. Okay, Internet Protocol became a standard. Sorry, I think I mistakenly clicked the wrong one. Okay, see this one in 1998, they are still talking about IPv4. This website, if you will read in it, there's no images at all. Very technical, very all text, a lot of text, sometimes hundreds of them. So simply, these are the people who are making all the internet technical parts. So these people, they had many proposals, many ideas. At the end, they agreed to move from IPv4 to IPv6. So the question now, where is IPv5? Okay, can you search? Can you ask Google, where's IPv5? We have IPv4, then IPv6. What happened to IPv5?
Only in experimental.
Yeah, experimental. So what happened? IPv5, it took a few months to decide that no, this is not a good idea. They moved directly to IPv6. IPv5, they have a few changes to do, but one of them, they decided that instead of 32 bits, IPv5 will have the double the bits. So to make it, say 32 multiplied by 2, that will give us 64 bits. If I go to my calculator again and check how much is that. So 2 to power 64, it will give us this a huge number. I don't know what's the name of this number. Don't expect me to know it. Very huge number. So they were like, okay, this is how much IPv5 we will get if we have 64. But directly they discovered that, oh, to change from IPv4 to IPv6, we have to change all the devices all around the world, which is taking very long time. They put 50 years to change from IPv4 to IPv6. But it seems that these 50 years are not enough to do it like step by step, you know? People start upgrading their systems. So instead of using IPv4, they will use the new one. However, 50 years, a lot of money, a lot of effort, a lot of engineers needed. So what if this number is not enough? Do we have to change again from IPv5 to IPv6? Directly, they said, no, IPv5 is not enough. Since we would do this big change, let's move directly to the next one. The next one is IPv6. IPv6. So directly they decided this one will be 128. Okay, bits. We do that one. 128 to the power 128. Let's see how much is that. 2 to the power 128. It will give you a very, 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 very huge number. Of course, if I couldn't read the 2 to the power 64, I would not be able to read this number as well. However, this number is very big. That's why you can see IPv4, we said 4 billion, this red one. The number we are talking about in IPv6 is this number of zeros, too many zeros. So you can see the difference between them. It's a very huge number. Now they said, after they choose 128, if every single bit of sand on this earth, bit of sand on earth, need an IP address, it will be enough for them. Okay. Every bit of sand on this earth need IPv6, they can get it. So that's why now every time they want to do changes to internet, they have to think about maybe 20 years from now, we get to new technologies, how we will handle these technologies. And those people who in you can see, let's see when was the IPv6, the idea when it was, we got Internet Engineering Task Force. You can see it was, oh no, this is not the last one. This is the main idea. 1998, they had the IPv6 main idea. At that time, we don't have AI, of course, is not there. We don't have smartphones. We don't have iPads. We don't have laptops at that time, no laptop. At that time also, there was no Internet of Things. All these technologies were not there, but they were predicting the future. In the future, we really need to be careful. We will make a big change, will cost a lot. So we have really to think about it carefully. That's why now internet people, they know that we don't design our networks only for now. We have to think about the future, what will happen in it. And we don't know what will happen, but we have to get ready. So now, for example, those who do the project on quantum networking. Quantum networking is a huge change. We don't know what is it. It's something mystery, but we know it will change a lot of things. We should get ready. Otherwise, the security will be an issue. Our devices will be an issue. Our safety will be an issue. Okay, we'll have some troubles. So that's the idea of IPv6. Not only the number, we had some other issues with IPv4 they needed to fix. IPv4, they had a problem with something called private IP address and public IP address. What is a private IP address and public IP address? Some ranges of IP addresses, they decide that, okay, since we don't have enough IPv4, okay, for IPv4, since we don't have enough IPv4, so let's put some ranges. Let's use private IP address. What is a private? Simply, if we are inside IIUM, we can use a specific identity card, the matric card. Every one of us, we have a unique matric card inside IIUM. But if you go outside IIUM, can you use the matric card, the matric number? Cannot, right? So inside IIUM, you may have 2513567. Okay, that's your matric number. Inside IIUM, wherever you go, this is the number you use. But at the moment you go outside the gateway of IIUM, that number is not valid. No one can understand it. Can we duplicate the same matric number? Can we have two students, one in IIUM students having a matric number of, let's say, 2427373? Okay, can we have that one in IIUM, another one in UTM having exactly the same one? 242 7373. Yes, we can. Because in that case, you just ask them, where are you from? IIUM. Okay, I know IIUM. I contact IIUM, then I will give them your number. But to give only the number 2427373, just give this number anywhere in Malaysia. No one will know who are you. Just inside your institute. So that's the main idea of the private IP address. But the problem with the private IP address, every time you need to talk to the outside world, you need to translate it. How to translate that? For example, this IIUM matrix number, outside, I think I added a number here, okay? Outside IIUM, this is belong to the ID, person with the ID, I don't know that, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this ID number. So every time you are outside, you will use this one. Inside, use this one. Someone from outside have this information, want to talk to you, they have to go to IIUM Ahmad, ask the database there, who is this guy or who's this guy? So you have to have a translator, someone translating the matrix number to the passport number or the IC number. Okay. Can you imagine if every time we want to talk about every student, we have to go to Ahmad? Okay. In that case, it will be a big headache, especially if that student is being asked about, I want to send him a message every single second. So the NAT, Network Address Translator, was one of the issues. NAT, Network Address Translator, was one of the issues. Because you have one gateway, you have to ask it about every single packet going in and outside IIUM. And of course, this NAT will be very slow. Security is not a good idea. Tracking people also is not an easy thing to do. So when they moved from IPv4 to IPv6, they said, okay, this is also a problem. Let's remove private IP address from IPv6. Since we'll fix it anyhow, let's fix everything. So they change the number of bits. That's the first change. The other change, first change is here. Number of bits was changed in IPv6. Another thing, no private IP address, no NAT. And the last one, what was the last one? Also, some security issues. They fixed it. The header of IPv4. Let's see the header of IPv4. I think I skipped that one fast. Okay, you look at the header of IPv4. Too many information inside there. They said, okay, this is complicating the switches and routers work. Instead of they have to figure out all these things, process them, check them, and so on, let's make the header much simpler. So if you check the header of IPv6, much number of fields, much less number of fields. Okay, so where's the IPv4? Is this one? This is the IPv6. Few of them, very straightforward, reducing the processing time inside the router and the switch. Now that's the main idea. Three things were changed: the header, the number of bits for IP address, and the NAT, no private IP address. Okay. Is everything clear up to this point? Am I going very fast? Everything is clear? Yes, no?
Yes.
Okay. Okay. If you are awake, can you raise your hand? Let's see how many of you are still awake. Twelve, 14, 15, 16 out of 29. So 13 of you sleeping. Okay. Not a good news. Okay, now let's go and continue and talk about the IPv6. I will not talk about how we write it and so on until we need it. For the time being, we don't. So we can skip the part of IPv4. Now for any device to, like this one, let's take this one. Okay, for any device, you have a message to send anywhere in this world. If I tell you now, I want you to send a message to Mr. X, who's living somewhere we don't know exactly where. Okay. I want you to send a message to Mr. X, who's living in, I don't know where. Send him a message. Can you reach that person? No, right? I'll tell you, send the message to Sister Sarah. Sarah, I don't know. Sarah Adam Smith. Okay, just a random name. If you don't know the location where exactly she's living, you cannot send the message. Same thing with the internet. If you don't know where to find that person, you cannot simply expect the router to tell you where to send the message you want to send to that person. I cannot put it there. For some reason, I cannot copy this one. Never mind. Screen, it's right here. Okay. My computer decided just to make troubles for me, you know. Never mind. So if we have a computer here, if we want to send a message from one computer to another computer, we have two things. You think about it like IIUM. If you want to connect to IIUM, okay, to send a message from KICT to Prof. Rafiqul Islam in IIUM, Kulliyah of Engineering. In that case, what you would do, you don't have to go to the gateway of IIUM, leave IIUM and come back. If our communication is inside, you go to the switch will send you here, right? Directly connect them. But if you are living outside IIUM, what you have to do, you have to pass by the gateway. In internet, the gateway is the router. The router is the gateway. So you go to the gateway of IIUM, ask about the person. I want to go to Kulliyah of Engineering in UKM. What you have to do first, you have to pass by the gateway. This is the gateway. Can you see the writing I'm putting there? Is the writing appearing to you? Can you see the writings? Whatever I write on
Yes.
the screen. Okay, because sometimes it will not appear. So if I want to pass from anything or send any message outside IIUM, I should pass by the gateway. The gateway is a router. The router is the gateway. Okay, I have to repeat that because later we get troubles. Then when you go to IIUM gateway, you ask them, I want to go to UKM. Oh, sorry, I want to go to, UKM. They'll tell you this is the direction to go to MRR2, for example, or Duke. And when you reach there, there is another gateway, ask about the kulliyah you want to, and it will send you to the server. Okay, now if by mistake, you try to go to Kulliyah of Engineering, however, what you do, you send a message to the gateway tell you go out, go all around the world, sorry, and then come back to IIUM. Okay, gateway, enter it, and then go to Kulliyah of Engineering. That doesn't make sense. That's why we need to know what is the local host, who's inside IIUM, and who's outside. How to know it? From the IP address. From the IP address, I can know if these people are in the same place or outside IIUM. So let's see something here. I'll stop this one. Okay. Now, if I have two addresses, one of them is, let's say, Prof. Rafiqul. I want to send him an email or a message. Prof. Rafiqul, he is in ECE department, College of Engineering, KOE. And then IIUM, Oba. And he's inside Malaysia. That's the address. Then my address is, I'm Dr. Zainab. At Department Computer Science, College of ICT, KICT, IIUM, Oba, Malaysia. Okay, looking at this one, are we in the same location or different location? Are we in the same campus or different campus? Same campus, right? How do we know that? Looking at this part of our address, it's the same. Now we have some other person, let's say Dr. Adamu. Dr. Adamu, he is in Department of Computer Science, KICT, IIUM, Gombak, Malaysia. Me and him, we share this one, right? So if you look at this one and this one, you know these two people are sitting in the same department, same building. But if you look at this one here with Dr. Prof. Rafiqul, these two people are not in the same buildings. Same thing for networking. We need to know which part of our address is showing that we are in the same place, same network, or we are in different network. That's why we have in the IP address, let's say we have 192.168.7.0. We will have something called subnet mask. Subnet mask here could be 24. What does that mean? It means those IP addresses sharing the same 24 bits at the beginning, they belong to the same network. They are not from outside. So now if I take this one, change it to binary, 192, what it will be? 11000000. That's 192 in binary. 168, it would be 101010000168. I remember it because I use it a lot. By time you will remember it as well. 7, it will be 0, 11111, 0, 0, 0, 0. Okay, that's the IP address we are having for. Okay, this is the IP address. Now, when we have the subnet mask, this simply is showing that the first 24 bits, if you're sharing exactly the same 24 bits, you are belonging to the same network. You don't have to pass by the gateway. You remember when we say you want to go to UKM, UKM is outside IIUM. So how to differentiate who's outside, who's inside? The subnet mask. Now, if we decide the subnet mask to be 29, it means that more portion of our network, of our IP address is representing the network. More portion, it's just like here, more, DCS, KICT, we share the same one, DCS, KICT. We are adding more part of the network to say this is belonging, or from the IP address, from the address itself, more part is showing the network portion. So this one, we call it network portion of the IP address. The part of the IP address representing the network. And the green one here, we call it the host portion. This is the part of the IP address representing a specific device. So inside the device, we will have two computers, one of them 192.168.7.3. The other one is 192.168.7.2. The other one is 192.168.8.3. Okay, let's put the /24. Looking at these IP addresses, which one is belonging to the same network? Which one is outside the network? Which one belongs to the same network? Which one belongs to different network? Remember, we said the first 24 bits. So if I change the, okay. The right one is an outsider. Yes, that's correct. Why? Because if I change this one to, if I change all of them actually to their binary, okay, let's do it. I don't want to type it again. That's why I will use just copy paste. First IP address, it will be 192.168.7.3. That will make this is 3. And to make it easy, the subnet mask /24, I will make it /24 from here. 24 of them, I will color it in different color. So these are in red. /2 will be, this is 1. Okay. /24. Now, the last one, look what will happen. 1000. This is in red. Look at it. You look at the network portion, it's different than the other two. The red part of our IP address is different. It means it's from different network, not the same network. If the red part, the network portion is the same, they belong to the same. They are in the same campus. They are the same building or whatever. Is it clear? This is that's 3. Is it clear up to this point? Yes. Now let's change the subnet mask. I'll make the subnet mask as /16. Will that change anything? Let's see /16. I will use the same coloring idea, /16. Okay, let's change all to black first. /16 means that the first 16 bit will be in red, or they are the network portion. So this is 816. This one, same thing. This one, same thing. So now the question, do they belong to the same network or different network now? Are they in the same network or different network?
Same.
Same network, right? Why same network? Because the network portion is the same. Network portion is the same. So that's why we need the subnet mask. When you write IPv4 or IPv6, you have to put subnet mask to see where are we going. Okay. Another way to write the subnet mask, if we have /16, if I have a /16 subnet mask, that means the number, this is another IP address. Subnet mask will be written as network portion all 1. This is another another address will be sent with the other one. 16 means that 16 ones, the rest are zeros. Okay, this IP address will be sent with this one together in your packet. And the switch will look at them, use the ANDing operation. add these two numbers to see, because of course we have the red and black, but if you go to switch doesn't know what is red and black. It will not understand it. And the switch cannot understand also /16. What they understand? Only binary number. So you send two of them. One of them, 16, 1, it represents /16. It represents the network portion. So it will know now when you to do the ANDing operation, it will know that this part is network. This part is the host portion. The device, switch, router, computer, this is how they understand subnet. Now we need to talk when we try to configure any device. The device again cannot understand /16. What they understand binary. But we human, we wanted to make, I will not write 000 every time. I need to change this number, all binary. I have to change it also to, for me to understand it, to a decimal number. So what it will be, this number, if I want to change it to decimal, what you will get? If you want to change it to decimal, what you will get? Okay, thank you, brother. It is 255, because we know when all of them are 1, 8 of them, it will be 255.255.0.0. Okay. So now every time we want to configure IP address, IPv4 address, what I would type inside the switch, I would type IP address. I will write this IP address. What is it? 192.168.7.3. Then beside it, it's supposed to be /16, but I cannot write /16. So what I will write? 255.255.0.0 when I try to configure any router. Okay, this is the command. So we have to write two numbers. One of them, just the IP address. The other one is, we call it subnet mask. Subnet mask is telling which part of the network is representing all the network, which one is representing a specific host. You can think about it. I can say KICT. Okay. KICT is not representing a specific person. Am I correct? KICT is not a specific person. It's not a specific location. So we have the whole network. But if I want to talk about a specific person, I'll say Dr. Adamu in KICT. Then you will know exactly I'm talking about a specific person inside a specific building or kuliya. So that's general. Okay, now another thing. When we said, let's take this one. I take this IP address. And we said this is 192.168.7.3/16. Okay. If I color it, this is the red part. Now, how many devices are inside the same network with this IP computer? How many devices can we have if we have /16? How many devices in KICT we can have, for example, if you have /16? Meaning that the host portion will change. So we will not have two devices exactly the same. First device in this network will be 000.000.000.000. In decimal, that will make it 192.168.0.0. That's /16. That's the first IP address we can have in this network. Is that correct? When all of them are 0. Next IP address, what it will be? Let's see. Next IP address, we don't change the red part. We just change this part. So if I want to change this one, I'll start from the one to the right, make it 1, which will make the decimal as 1. Okay, next one. But it will be the next device, the next IP address. When I change this one to 1, and this one became 2. What is the last IP address? Can you tell me? In binary? Inside this network, what will be the last IP address? I take the red, the network portion, 16 of them, make them in red, never change them. So what will be the last IP address I can use? Exactly, thank you, brother. It will be when all of them are 1. All the black colored, the host portion, all of them are 1. Okay, that's when we will have the network. So this is the range of IP addresses we can have inside that network. Okay, starting from when all of them are 0, ending when all the host portion, not the network portion, all of them are 1. Okay, now we have 2 IP addresses of these. The first one is reserved. We cannot use it. This one, we cannot use it. And the last one also, we cannot use it. For every network we have, the first IP address, not allowed. The last IP address, we don't use it. The first IP address, we call it network ID. This is reserved. No specific host can use it. It's just like when I said about KICT. So I said KICT is a name for the entire Kuliya. I cannot say KICT, I mean a specific person. Same thing here. When all of them are 0, we are talking about the entire network, not a specific device inside the network. And this one here, we call it broadcast address. What does that mean? The last IP address, when all of them are 1, we call it broadcast IP address. What is that IP address? Why do we need it? Any idea? Okay, network ID, I'm representing the entire network. We know this one. Broadcast IP address, it is an IP address we will use as a destination IP address if I want to send a message to everyone. Okay, IP address, if I send the message to this one, it means everyone inside this network will receive that message. So no specific device can have it. If I try now in Packet Tracer, to take time to open as usual. If I try to assign these IP addresses to any router, to any switch, it will give me an error. So if I take this one, a router, okay, and go to it, give it a time to open, and I will take another computer also, put it here. No need to connect them now, it's just we are talking about very general idea. Okay, give it a second, then we can use the router. It's booting, okay, no. So inside here, I will talk about what we are writing about the configuration later. I will go to a specific interface, give it an IP address. But before that, I need to see show IP interface. Okay, we have interface called G00. So I will go inside that interface, G000. And in here, I try to put IP address. I will use 192.168.0.0, the one we said we cannot use. Let's try that one. See the one we cannot use? This one, .0.0/16. /16, it means 1111, 16 ones. right? 16 ones followed by the rest of them are zeros. That's what it means by slash 16. So change this one to decimal. What you will get? You will get 255. I don't want it to. Okay, 255. How to do this one? Okay, if I have this one, which is slash 16 at the end, okay, change it to decimal, you will get 255.255.0.0. Okay, go back here. So I need the slash 16, cannot write slash 16. See, if I try to do it, it will give you something wrong is happening. I cannot understand what you are saying. It will give you this sign, small sign, to show you that the router couldn't understand what you are talking about. That's mean the IP address is wrong. 255.255.0.0. See what you get. Bad mask for address. It means that if you are using this address, 192.168/0/.0.0, you cannot use it inside the device. If you try to change the subnet mask, let's make it /24. It will have the same issue. Okay, but if you change it to any other number, let's say 1 or 2, you will get no error. Okay, everything is fine. Let's try the computer. If I open the computer also, go to desktop IP configuration. From here, I type 192.168.0.0. Directly, it will give you error message. Invalid IP for this subnet mask entered. You are not allowed to use IP address. Same thing, let's try to do the other one, the last IP address, 192.168.255.255. Same thing. Tell you this cannot be used as IP address. So choose any number. This is what it's saying. Choose any number in this range, but not the first one, not the last one. I can use 1, 2, 3, 4, up to 254. So if we have that's the case, it means that the number of devices we can have in this network, it will be 2 to the power 16, because 16 bits, right? 2 to the power 16, all of it, minus 2 IP addresses we cannot use, the first one and the last one, which will give, if we have /16, how many devices we can have in that network. 2 to the power 16, let's ask the calculator. 2 to the power 16 will give us 65,536. 65,536. I think I forgot. What is that? 536, yes. Minus 2. Minus 2. Which will give us 65,536 device inside /16 network. Okay, so that's simply the beginning of next class subnetting topic. I hope it's clear now why we need subnetting, how it will change the network ID, how it would change our network size. Okay, this is what we tried to talk about today. Next class, inshallah, we will talk about more in subnetting. Hopefully, we can finish all the subnetting next week, inshallah. Next class, inshallah. Okay, any questions? Is it clear? Is it clear? Everything is okay?
Yes.
Okay, alhamdulillah. Okay, so if it's clear, let's stop here because it's the end of the class. Inshallah, I will see you next class. If anything is not clear, you can write in the chat box. I'll stay here 1 more minute after everyone leave. Or you can write in the WhatsApp group. Don't forget the attendance. It's your responsibility. If you are here, I will check the attendance, actually compare between the attendance in Microsoft Teams and the attendance you put in Italian. You have to put in Italian. Here it will be signed automatically. Hopefully no one was signed in Italian, but they didn't attend the live session. Hopefully. Okay, thank you very much, and Assalamu alaikum.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Okay, if there's no question, we can end here. Assalamu alaikum.